Okay, so a particle of mass 0.1 kilograms is initially stationary. A single force F acts on this particle in direction parallel to the vector 7I plus 24j. As a result, the particle accelerates in a straight line, reaching a speed of 4 meters per second after traveling a distance of 3.2 meters. Find F. There's a lot going on here. So let's draw a little diagram. 0.1 kg. You've got the weight of this particle, which is 0.1 g newtons. You've also got the force F acting on it, so that's going 7I in this direction, so 7 newtons in this direction. Or actually, no, we don't even know the size of the force. We just know that there's a force acting in a certain direction. 7I24j. Okay. As a result, the particle accelerates in a straight line, reaching a speed of 4 meters per second. It's initially stationary. Okay, so what we can do here is actually we can work out the acceleration with suvat, and then we're going to be using F equals ma. So we've got SUVAT. S, which is our displacement, I guess, in this case is going to be 3.2. It reaches a speed of 4, so its final velocity is 4. Its initial velocity is 0 because it says it's initially stationary. And we can work out the acceleration from here. So we can use an equation that involves S, U, V, and A is V squared equals U squared plus 2AS. So we can rearrange this to have V squared minus U squared over 2S equals A. So we have 4 squared minus 0 squared over 2 lots of 3.2, which is 6.4. So that is giving us 16 over 6.4. So if 16 over 64 is 0.25, then 16 over 6.4 is going to be 2.5. So our acceleration is equal to 2.5 meters per second squared. Okay. So we now know the acceleration. If this force is acting in such a direction, then yeah, we must have to consider all the forces that are acting. So this is F. Okay, so what we actually need to do here yeah. So what we need to do here is resolve the forces. Or do we? Am I overcomplicating this? No, I don't think I am. Actually, let me get a hint from how many marks this question is worth. It's only worth 5 marks. Okay. It's only worth 5 marks. As a result, the particle accelerates in a straight line, reaching a speed after traveling. Okay, so we do this acceleration. Oh, okay, this is weird. So it says a single force, F. So that means then that we don't have to. Okay, so we don't need to incorporate this gravity business happening. It's just a single force that we need. And they gave us the mass because we can work out we can use F equals ma basically. So I was overcomplicating it. So we don't need that information that I added there. So we can use F equals ma. And we know that, well, we don't know F, but we know what mass is, which is 0.1. And we know what the acceleration is, which is 2.5. So therefore, F is equal to 0.25 newtons. So it must be that this mass is on some sort of table or something. And on that table, horizontally to the table, it's being pushed in a direction that's parallel to the vector 7i plus 24j. So the direction in which the weight of the ball acts in is perpendicular to both I and j. So we don't have to consider its movement, if that makes sense.
Yeah. Wait, can you repeat that again, please?
So basically, you've got your how would I draw this? Okay, so you've got, let's just imagine this is on like a table of some kind. This ball is on the table, and you've got the force which acts like 7i24. So it's like roughly this direction. If you imagine like this being your I direction and this being your j, the ball's acting somewhere in between. Does that make sense?
Yeah.
And then the weight of the ball acts this way, which is perpendicular. So it's got nothing to do with the movement of the ball. Because I initially included the weight, thinking that the force, thinking that the weight would be part of the resultant force, but it's not, because it's acting in a different plane altogether. It's acting through the table, if you like, as in perpendicular to the table or at right angles to the table, whereas the force that's causing this particle to move is acting parallel to the table.
Okay, I think I get it.
Cool. But this is another one of those ones where I feel like there definitely should be more information, as in another part to this question.
So why did they give you a vector then?
Well, that's my thinking exactly. There must have been something. There must have been something that was needed. Like there must be another part to this question.
Oh.
There's got to be.
No, we didn't get the second part.
Because the only other thing that I can think of is that they want us to work out the magnitude. No, the actual vector of f.
I have the mark scheme.
Ah, okay. So my thinking, okay, I see this 7, 24, 25. So if this is the result, if this is the magnitude of the force, the vector would then have to be 0.7 I plus 0.24 j, or the vector 0.7, 0.24. The only reason I spotted that was because in Pythagoras' theorem, one of the Pythagorean triplets is 7, 24, 25, as in 7 squared plus 24 squared is equal to 25 squared.
Yeah.
And so we've worked out the resultant force, as in the actual magnitude, to be 0.25 newtons. But because it says it's F is acting parallel to the vector 7i plus 24j, if the resultant force is 25 newtons, then the two forces themselves would be 0.7 in the I direction and 0.24 in the J direction, because so this is our final answer, or this one, 0.7I plus 0.24J, either one is fine. But we know that 0.7 squared plus 0.24 squared is equal to 0.25 squared.
Oh yeah, that's what it says to do here on the mark scheme.
What does it say?
It says you calculate the magnitude of the given vector and then deduces using given information correct vector form of the force.
Mm-hmm. Yeah, that was quite an interesting one. Yeah, because it was making the connection with 724. Because when I saw 724, initially I thought, oh, Pythagoras, it's one of those triplets. But then I realized, oh, how come we've not made use of it? And then at the end, of course, because F itself is a vector, forces are vectors.